We have almost come to the end of the course, and probably this is the last class, I guess, unless if there is something which I would like to summarize later, but probably this is the last class. And since last class we have been discussing previous class about pure shift NMR, another interesting topic. What is a pure shift NMR? For that I just introduce you what are the key factors of NMR. One is sensitivity, other is the resolution. Of course, there are ways to address the sensitivity by going to higher magnetic field, increasing sample concentration, and also adapting polarization transfer experimental methodologies that we discussed. What about the resolution? One thing for the resolution is we can also go to higher magnetic field. Higher the magnetic field, larger the chemical shift dispersion, you get better resolution. That is one way. But what happens in some complex molecules? This complexity comes because of large number of couplings. What are the large number of couplings? It can be heteronuclear or homonuclear. In the heteronuclear case, I said you can reduce the spectral complexity just by doing what is called the broadband decoupling. When you do the broadband decoupling, you will break the coupling of all heteronuclei dilute spins with the abundant spins like proton, like carbon 13 decoupled with protons. Then you get individual peaks for each of the carbons, one way. But what is the loss there? You get better resolution, you are reduced, but you have got rid of the coupling information. That is important thing. Coupling is a useful information. By doing decoupling, you simplify the spectrum, reduce the complexity, but you have lost the spectral information. Doesn't matter, but in many examples, when the spectral complexity is very important, simplifying this to identify chemical shifts, if it is an important condition criteria to assign the peaks, and then of course you can worry about getting the J coupling information from the multiplicity later. If you want to get the chemical shift information, decoupling is one of the options, broadband decoupling. Okay, in the case of heteronuclear, broadband decoupling is easy. I told you, we have seen that carbon 13 several examples, and you can do for this for any other nuclei also. Broadband decoupling is easy, especially when there are two nuclei completely different, because you can hit the frequency of other nuclei while observing the different nuclei. There is no interference between these two, because they are all megahertz away separation. Frequencies are separated by several megahertz. That's okay. But what happens in the case of the proton? If I have to do the proton NMR, then we will understand the proton NMR and its complexity, how we can overcome that in this class. So we will start with let us looking at the complexity of the 1H NMR spectra. Why does a complexity comes? First thing, chemical dispersion is very small, about 10 ppm maximum. In a 10 ppm range, let us consider 500 megahertz spectrometer. 10 ppm is 5000 hertz. In a 5000 hertz range, if you take a reasonably big molecule with at least 10 to 20 or 30 different protons, each of them interacting with other protons, then there will be a lot of complexity because of multiple couplings experienced by each protons. Multiplicity become bigger. More and more multiplicity will be there, more and more couplings will be there. And also because of this poor chemical dispersion, there is extensive signal overlap. Signal overlap will be so much, you will be very difficult for you to identify the chemical shifts. Okay, so in many of the examples we took in the analysis of the proton spectra and other heteronuclei, they were all fairly simple. If you got a slightly bigger molecule, it is not easy if the multiplicity becomes more. So complexity of the spectrum comes because of poor chemical shift dispersion, and each spin experiencing pairwise interaction among lot of other spins, which gives rise to extensive signal overlap, complicating the spectrum. All right, what can we do to overcome that? Like I said, in the heteronuclear case, we can do broadband decoupling. Of course, we can lose the coupling information, but to simplify the spectral complexity, can we do broadband homonuclear decoupling of protons like we did for heteronuclei? This question, of course, if there are challenges, of course, if you can do that, you can reduce the spectral complexity, we can get a better resolution. interpretation of the chemical shift become easy. You can identify which proton, what is the chemical shift of each of the individual protons, because when you remove the complexity, each peak corresponds to the particular chemical shift of chemically inequivalent protons. There is an advantage. But what is the disadvantage? You have lost chemical shift information. Coupling information. You have lost the coupling information that is very useful in getting the conformation of the molecule. Remember I told you about this Carpus equation where 3J coupling can be used to get the conformation. There is a disadvantage. We lose that. So it does not matter. But how we can do that in case we are going to compromise only for the chemical shift information and we are not worried about loss of coupling information. How do you overcome this? There is a challenge in broadband decoupling of 1H protons. What is the challenge? When you are doing the decoupling, you remember I apply a decoupling power. In the heteronuclear case, I was applying detecting carbon 13, applying a very high RF power, CW power or with different pulses at the proton frequency such that we can break the coupling. But here what we are doing? It's a broadband decoupling of proton while we observe the proton. That means, remember what was the sequence of carbon 13? We apply the carbon 13 to this thing, start collecting the signal, but in the proton simultaneously we are applying decoupling power while detecting. Remember, you have to apply the decoupling power at the time of detecting. That is a challenge here. So broadband decoupling power during acquisition, when you apply RF power on proton while detecting proton, it will destroy all the transverse magnetization. It will complicate the issue. So broadband decoupling of the proton spins while simultaneously detecting the protons is a challenge. It is not easy, it is not possible. Of course, you can do it different ways, indirect ways, but directly by decouple proton by applying simple RF power, CW power and detect proton is not easy. It is a challenge. So broadband decoupling is not possible, especially for the protons. I am talking about proton. Broadband decoupling of proton while detecting proton is a challenge. What people do at times in the good old days, we were doing what is called frequency selective decoupling. What do you mean by frequency selective decoupling? I can irradiate at a single frequency and see the change, what is happening at the other part of the spectrum. I can irradiate several frequencies at a time and see the change in the spectrum. You can do that. Then that type of decoupling helps you to identify which proton is coupled to which proton. I can simplify that. That was the way method adapted to identify the coupled partners. How we do the homonuclear selective decoupling? Exactly what we do for the broadband decoupling. Only thing is we saturate this particular proton signal. Selectively saturate one of them. Apply proton on one of the RF power on one of the protons and saturate that proton. Then apply RF for the other proton for detection. Or a conventional way, saturate a proton and simply detect the signal. After applying RF on a selected proton, collect the signal and see the change. That is what is being done. What happens if you do the frequency selective decoupling? Look at it, I have a 2 coupled spin system, AX. This center gives you chemical shift, this center gives you chemical shift, and this separation gives you J coupling. Alright. What we are going to do? We selectively saturate this peak. You get a singlet because I am breaking the coupling between this and this. I know then this is coupled to this. That is okay. I get coupling information, but you see I simplify the spectrum. So simplify the spectrum, doublet becomes singlet. This is a frequency selective decoupling. Okay. For a small molecule, fine, you can do it. What happens if your molecule is very big with n number of protons, large number of protons? Selective, this type frequency selective decoupling is a challenge. First of all, you have to have a perfect frequency selection and you have to apply RF so that neighboring peaks are not disturbed. And also it is strenuous experiment. You can do several such experiments, you have to do hundreds of such peaks you have to irradiate. That is okay. But it is a difficult job. But you can do how we do is like this. Select the 2 protons which is coupled. Let us say I am irradiating X proton, you can get the doublet of A, like what I showed in the previous slide. When we do that, depending upon the RF power where we are hitting and what is the RF power. See, in the decoupler offset I have to set perfectly on the other coupled partner. For example, this is a doublet. I have to hit perfectly the center of this one, then you will see the change here. But if the decoupler offset is far away, then efficiency will not be very good. So decoupler won't be efficient, you see. As the offset becomes larger and larger here, decoupler offset, the coupling strength will not be removed, coupling will not be removed. Only thing is there is a reduction in the coupling bit and but only one is exactly on resonance at a particular chemical shift at the of the coupled partner, then you will hit that with second RF, then you are going to get a singlet, then you break the coupling. So it is a selective decoupling. So and when you do selective decoupling like this, there are many complications like this. This type of thing is called Brock-Seeger shift, you don't worry about it. So this is what we discussed in one of the previous courses, I will not go into that. But also we can do one more experiment called multi-site decoupling. It is another experiment, but little cumbersome experiment. Why it is cumbersome? Take the example of menthol here. You see, we can look at the proton here, one of the protons. Look at this region here, this region which is expanded here. It is looks like quartet of a triplet or something like that, whatever we are getting. Looks like that at a pentet of a triplet, what some funny pattern is there. This is coming for what? Coming from which region? We do not know. Which proton is it? It is experiencing coupling with several other protons. Okay. Now this is, I want to identify and simplify this complexity. We selectively irradiate proton 1 here, and you see changes here. This became 2 triplets, doublet of triplets. Further, selectively irradiate at proton H1 and H8, which is H1, this is H1 and this is H8. See, now the complexity became much better. It instead of a doublet of triplet, it became doublet of doublet. Go further, you can saturate this, he irradiated H1, H3A and H8, all the 3. Then you are going to get the coupling between this proton, you are going to see the coupling here, that is now a doublet. You can simply measure the separation and get the coupling, 3 bond coupling. See, this is very easy. But what we did is multiple decoupling, multi-site decoupling. We are irradiate RF power simultaneously at 3 protons, and every time we saw change in the complexity pattern, and finally we are going to get a doublet like this to measure the couplings in a straightforward manner. This is one way. And of course, we can also do the broadband decoupling of protons, is possible by adapting certain experimental methodologies, not straight away by hitting with RF power like this. As I told you, decoupling proton while detecting proton is not a easy thing, it is a challenge. So one of the easiest way of you can think of, if you do the broadband decoupling, what is the advantage? Of course, why we have to do is the advantage is resolution. I will tell you what is the resolution you are going to get. Consider a molecule like this. I look at proton, don't worry about symmetry and everything. I assume that there is a symmetry is not there, X and Y is there or something like some. If you break the symmetry, assuming there is no symmetry, this CH proton is coupled to 2 CH3 protons of equal strength, let us say 10 hertz, then it is going to be a septet. Septet is a 7-line pattern. Each line is separated by 10 hertz. So what is the width? From one end of the peak to other end of the multiplicity peak, if you consider, it is going to be 70 hertz. Assume that I am going to do the decoupling, and after decoupling, the natural line width is 2 hertz. What does it mean? From this end to this end, there are 7 peaks. You measure the separation, each is 10 hertz, 10 hertz like this. This let us say about 60 hertz or whatever you get. And then if you do the decoupling, you get 2 hertz line width. That means this multiplicity pattern has been reduced to single peak of line width 2 hertz. What does it mean? It amounts to telling that the line width has come down by 30 times. The signal to noise, this reduction in the line width is 30 times. This means in an alternately I can say I have got the high resolution spectrum of the same thing without decoupling at 9 gigahertz, analogous to that. If you get a high resolution spectrum at 9 gigahertz, then they are all this multiplicity pattern will be highly dispersed with only 2 hertz line width, then it is easy to see that. So, analogous of this decoupling, broadband decoupling can be compared to the recording the spectrum in a very high field magnetic field, high field spectrometer. So, resolution improvement is almost an order of magnitude, and this is what it is. In a pure shift NMR, if you do that broadband decoupling, this is the spectrum, complex spectrum. Look at this complexity in this region. When we do this broadband decoupling, each peak corresponds to single peak. There are so many protons are there, each of them gives the particular chemical shift of each of them. So, all this multiplicity pattern disappears and we are going to get. This is as good as telling I have got a, instead of 500, this is the spectrum, let us say is at 500 megahertz, I would say this is we have obtained this spectrum at 5 gigahertz, as good as obtaining the spectrum at 5 gigahertz resolution. If you obtain this spectrum at 5 gigahertz, you get this type of resolution. You can imagine like that. It is a comparison. All right. Let us say I want to do the broadband decoupling. What are the approaches? How do you do that? When I say broadband decoupling is a challenge, how do you do that? There are two ways of doing. In the 2D experiment way, where I can do the broadband homonuclear decoupling in the indirect dimension, or I can also do the broadband decoupling during acquisition, which is even more challenging. Just now I said, while during acquisition, you cannot do the broadband decoupling, it is a challenge, but of course we can do somehow. There are two ways of doing broadband decoupling, homonuclear decoupling in the indirect dimension and also in the direct dimension. All right. The way you are going to get broadband decoupled, homo decoupled proton spectra are called pure shift spectra. That means couplings are completely removed. What you are going to get is only chemical shifts for each chemical inequivalent proton, a single peak at each chemical inequivalent proton, and that type of spectra what we saw before just now I showed you here, they are called pure shift spectra. So, this is the way you can get rid of coupling information and get sharp lines with highly resolved spectrum. This is called pure shift spectrum. Okay. And what is simplest way of doing this broadband decoupling? Remember when I talked about J resolved experiment, I said in the J resolved experiment of homonuclear, we saw that there is delta plus J information here and J information in the indirect dimension, and this spectrum we saw it is tilted by 45 degree. It will be like because the both J and delta are here, but same thing if you do the tilting by 45 degree and take the projection, we get a single peak. The triplet appears like a single peak. Remember we discussed this when we discussed J resolved experiment. So, projection of the 45 degree tilted J resolved spectrum is nothing but the broadband decoupled proton spectrum, broadband decoupled proton spectrum. That is one way. So, I can call it as a pure shift spectrum because no J coupling information. So, you can have n number of peaks, n number of couplings, each of them, do the J resolve, take the projection. This is what is called a pure shift spectrum. So, simplest possible way. But there are certain issues in that when you have strong coupling efforts, etc. We will not go into more details. But what is done in the pure shift experiment is something important. Spins are manipulated in such a way, the average evolution of the magnetization is only under chemical shift. We have to manipulate spin dynamics, we have to manipulate such that the spin magnetization evolves only under chemical shift where J couplings are removed or refocused, or it should not evolve. Something we can do. We will ensure J couplings do not evolve or refocus even if evolve, or it somehow get decoupled. That is the way we can do. But to do that or to prevent the evolution of J coupling, there are two possible ways to obtain pure shift spectra. One is refocusing of J evolution, other is what is called a constant time experiment. When you do constant time experiment, J coupling do not evolve. When J coupling does not evolve, it is as good as only chemical shift evolution. That is one way. One way you can refocus J coupling, prevent evolution. Other way you do constant time experiment where J coupling do not evolve at all. There are two possible ways. There are many ways. So you can this thing I am telling you. If you do the J refocusing, what we do, the first we say spins are inverted. Let us take active spin. One of the phase of the one of the passive spin which is not coupled, select one of the spins which is active spin. All the other passive spins are inverted. What will happen? All the passive spins are inverted. Active spin phase remains unaltered, remains same, unchanged. Then what will happen? Active and passive spin coupling is broken. That means it refocuses the coupling between active and passive spins. What it means is, in J refocusing experiment, simply understand spins are inverted, passive spins are inverted, phases of the active spin remains unaltered. This refocuses the coupling between active and passive spins. That is what it is. Then we say active spins are decoupled and we are detected. Alright. How do you acquire the data with J refocusing? Is the next question. We can do J refocusing, let us say. How do you acquire data while doing J refocusing? What we do is we acquire chunks of FID, okay, and that was acquired independently for a particular time, which is 2 over J. With J refocusing, J refocused at midpoint of each. We have a different chunks of FID chosen and series of chunks are acquired, concatenate each of them and construct a composite FID and do the Fourier transformation. That is one way, like collecting the chunks of FID, and each time at the midpoint of it we have to ensure that J's are refocused. Take the several such chunks, artificially you concatenate, bring them together, make it construct a composite FID, composite all these chunks as an FID and do the Fourier transformation. That is what we do. Then chemical shift, J couplings in such a situation will not evolve. The FID has only chemical shift evolution. J is refocused at each of the center of each of the chunks which you say, chunk of FIDs. Small FID chunks you take and at the center of each of them J couplings are refocused, only chemical shifts will evolve. That is okay. So concatenate FIDs Fourier transform and you get a pure shift, and large number of such chunks if you take, of course large does not mean a big number, about 20, 30 or 40 chunks is more than sufficient. Beyond that FID would have died down. Even 30, 32 is very difficult to get it. But that if you take that many number of chunks you get narrow peaks. If you have a smaller number of chunks you get broad peaks. So narrow lines will come if you have large number of chunks. And of course if chunk size also matters, shorter chunks will give, will generate cleaner spectrum, and as there is as the maximum deviation from J coupling, exact J coupling is reduced. There won't be much deviation. And there is also what is called a direct detection approach. That is very important, very interesting thing. This is in which case while acquiring the signal we can apply J refocusing elements in between the FID. I am collecting FID like this. In between I can put J refocusing at several places and collect the FID. At these places what will happen, if there are n number of such things applied in bit while collecting the signal, in each of these the FID refocusing element J gets refocused and whole FID is acquired in a single shot. But then while acquiring the data J's are refocused. So there are several J refocusing elements. What are the refocusing elements? Like bulk frequency, anti-geocozy, time resolve, so many things are there. Each of these J refocusing element reverses the effect of J and then suppressed at a given evolution time. That is the important thing. Of course constant time experiment is what is normally done, of course very often. In the constant time experiment what is done, the evolution time is kept constant. In the 2D experiment I told you there is evolution time and detection time. The evolution time is always kept constant with a particular delay, let us say t. In between you apply 180 pulse, you know it like a spin echo. When you have a 180 pulse, homonuclear, J will get, chemical shifts get refocused, J will continue to evolve. But what will happen is, don't allow the J to evolve. You apply 180 pulse at the center, instead of incrementing the T1, you change the position of the 180 degree pulse. Don't increment T1, you change the position of the 180 pulse, keeping this constant total period. In which case what happens, the 180 pulse is positioned after a let us say particular time, followed by this delay. This ensures, then what will happen, there is no J modulation. So chemical shift only evolves during T1. This is called a constant time experiment. Homonuclear scalar couplings are not influenced by 180 pulses and evolves during total delay, but then coupling is not getting modulated as a function of T1. So evolution of J coupling in the indirect dimension is completely prevented. This is called a constant time experiment. Okay. Then you may ask me a question, what about carbon-carbon homonuclear couplings? Their very abundance is very small. Carbon-13 coupling 1 in 10,000, that will generally will not be worried. So they are not popular. They are very popular only in the constant time HSQC experiment, but not for homonuclear experiments. So 2D experiment of such a, if you take a 2D spectrum of such type of experiment you do and Fourier transform, you get a 2D spectrum, you get a pure shift spectrum. In the constant time experiment, T1 dimension is kept constant, and then acquire the 2D data, keeping T constant, varying is moving the 180 degree pulse in such a way, you will have the incremented T1, but total period remaining constant, and do the double Fourier transformation. In the indirect dimension, you are going to get 2D spectrum which is pure shaped, and you get conventional spectrum in the direct dimension. And also another way is bulk decoupling. We discussed this when we discussed the carbon-13 NMR. What does bulk do? I told you bulk decouples carbon-13 bound protons from carbon-12 bound proton. That also I told you, it selectively inverts carbon-12. Pictorially we understood how the polar vector in the vector diagram, how it works. Its carbon-12 bound protons are selectively inverted, while carbon-13 bound protons are unaffected. We saw that when we discussed bulk, especially bulk decoupling, when we try to do HSQC, HMQC, etc. Following that, inept filtering is done to suppress the signals arising from carbon-12 protons which are not coupled, which are not decoupled. So finally, frequency and spatially selective decoupling you can do. The advantage of that is, another experiment, you apply a linear gradient along the sample. That is very interesting. When you apply a linear gradient, what happens? Different regions of the sample experience different magnetic field. For example, this is your NMR tube. Apply a linear gradient along this axis. Then each part of the sample has a different magnetic field because there is a gradient. When you have a different magnetic field, the resonant frequencies are different. So you get location dependent frequency shift. Then each area, each part of the sample experience different magnetic field. So this results in location dependent frequency shift. Okay. And the frequency and spatially selective decoupling one can do by concept called Zanger-Stark method. This is a very famous experiment given by great scientists Zanger and Stark. And what they do is like this: in the NMR sample tube, sample is there in the NMR tube, apply a gradient along this axis, and then a selective pulse during the gradient. If you do, then what happens? Different part of the sample in different slices, different spins are excited. Essentially, the whole spectrum is excited by a selective pulse during gradient. This is what you can do. You can apply a selective pulse during gradient and excite the whole spectrum at a time. And the selectively excited signals then are decoupled by inverting all other spins. And this is how do you achieve this? For this, the proposed pulse sequence proposed by Zanger and Stark are combination of two pulses hard pulse and soft pulse 180 pulses of the same strength during the gradient field. And this is what the pulse sequence of Sanger and Stark, combination of hard pulse and 180 soft pulse, both are applied, and then this is period is kept as T1 by 2, and instead of, when you do that, select applying this 180 pulse hard and soft pulse, we can do selective decoupling here. As I said, you can do deselectively, inverting all other protons, you can do the decoupling, homonuclear decoupling can be achieved. And you may ask me a question, fine, we can do the decoupling, what is the strength of the gradient, how much you have to put? Oh, these are all more of the details, you don't worry about it. Finally, I tell you how to create a one-day FT. Scalar couplings, you should know, evolve slowly compared to chemical shift. Why? Because chemical shift interaction strength is larger. J coupling is of the order of 5 to 10 hertz at 15 hertz in homonuclear proton-proton, whereas chemical shifts of the order of several kilohertz. So they evolve faster, chemical shift. Scalar coupling evolves very slowly. As a consequence, we collect the free induction decay initial portion of the FID for a short time before chemical shift, J coupling starts coming into the picture. If you collect FID, only you have chemical shift information in the initial portion of the FID. Let us say J coupling takes some time to evolve. Here in the beginning portion of the FID, chemical shift would have evolved. Collect only this much, then there won't be any interference on the J coupling. So this is the important idea to do that. How do you create the FID? Initial points of each FID is taken, arranged as a new FID consecutively, and then you do the Fourier transformation. New FID is Fourier transformation, and this is how it is done. Different FID chunks are taken, assembled here like this, and then do the Fourier transformation. This is indirect way. Several times, you will have this for T1, and each time you collect the FID, different chunks like this, and then after assembling this, you will get a real assembled FID, chunks of FID like this. And what should be the size of the chunk? Remember, it's 1/2 times SW1. What is SW1? Is nothing but the width of the J split multiplied, widest J split multiplied in the spectrum. Find out what is the largest split. For example, I told you the multiplicity pattern is this much, and this spread is 25 hertz. So this SW, or the size of the chunk should be 1/2 into 25, 1/50 hertz. That should be the size of the chunk. Okay. So number of T1 increments also depends upon how many chunks you want. Usually, as I told you, it cannot be more than 32 or 64. 64 also is too much. Around 32 chunks or so we collect, concatenate the FID and start collecting the signal. This is how it is done indirectly. That is one type of experiment. Other is, I told you, the real time spin manipulation. As one of the two ways of doing, I can do in the indirect way or in the direct dimension spin manipulation. That is what I told you. How do you do the real time spin manipulation? It's very easy way. I can do the homonuclear decoupling by using bird or some single FID or something, some JK refocusing, and acquisition is interrupted after every little bit every interval, and we can perform either selective or bird decoupling while acquiring the signal like this. This is acquisition and decoupling alternated n times. See, you acquire the signal, in between you use a JK refocusing, again acquire signal, J refocusing in between like this. Keep on repeating this n times, whole experiment n times. All these several chunks of FID together gives an FID, this final FID like this. In between FIDs, this chunk is there. This is what it is done. If you look at it, the real time manipulation is like this. It is a FID in principle. If we don't do any J refocusing in between, this is the type of spectrum you are going to get. But we can refocus with a window several times in between. This is a refocus window. And then if you collect this FID, you are going to get an FID devoid of all J coupling. You get only chemical shifts. That is nothing but a pure shift experiment. In which case, you don't need a special processing technique. Remember, I forgot to tell you, in all other previous experiment where you concatenate the data, assemble it and do the Fourier transformation. There are special pulse programs required to concatenate and do the processing. But in this direct detection there is no such things. There is no special data processing technique required. Directly you acquire the FID, while you have, when in between at different intervals you do the J refocusing, you are going to collect the signal and do the Fourier transformation, get a simple spectrum without J coupling. And this is an experiment where we can do this type of decoupling and different intervals J will be refocused. Okay, this is the famous Glass and Zanger experiment. So, decoupling is achieved by a combination of hard and band selective 180 pulse, and the gradient strength of same strength is using during excitation. Of course, there are certain troubles in this type of experiment. When you do this J resolved pure shift experiment, it is not easy, especially when you do this type of direct detection experiment. What will happen is, while acquiring and interrupting the FID because of decoupling due to J refocusing, at the same time magnetization is also relaxing, that gives rise to artifacts, and pulses should be very short, as otherwise large, especially for large molecules there have a shorter T2 relaxation times, signal would have relaxed before that. So, all these things will have to be taken into account, and then it will give rise to some artifacts in the spectrum. There are certain artifacts, many times unavoidable artifacts will be there, some can be avoided. Okay. So, with this I show you a simple pulse pure shift spectrum of a molecule called azithromycin. Okay. This is taken from the one of the papers of Gareth Morris group. You can see this region is expanded here. This is conventional spectrum, this is pure shift spectrum. Okay. This is instant homo decoupled spectrum, that means while decoupling while doing acquisition, and conventional way of Zanger stuck pseudo duty way of decoupling would have taken more than 10 hours. This is direct detection. Same thing what I said, like a earlier way we can create a 2D way by indirectly, either by using CT constant time experiment or J focusing elements you put and do a 2D experiment, that would have taken lot of time. But this convention direct detection experiment, while you are interrupting the FID simultaneously at different intervals for J refocusing would take only small time, and this is a typical experiment. You see, this is a toxic experiment. I tell you, where do you find the utility of it? In simple example, in our own study, in our own molecules, this is a molecule we are looking at it. If I take the proton spectrum here, we have proton and fluorine couplings both present in this case. Which are the FH couplings here? In this, if you analyze the spectrum, you cannot directly say which is FH coupling unless there is only one fluorine coupled to a single proton, but each of them have a proton-proton coupling and also proton-fluorine couplings. Look at this is spectrum. This spectrum is pure shift spectrum where homonuclear HH couplings are removed. Then what are you going to get here? You get only FH couplings. Each of them now, if you measure the separation, you will get the FH coupling. Direct extraction of FH coupling is possible in the pure shift experiment. Okay. So, this is another advantage. And look at this molecule, we have phosphorus here and proton-proton couplings. This spectrum has both HH coupling and pH coupling. Both phosphorus proton and proton-proton coupling complicate this spectrum. Do the pure shift here, HH couplings are removed. Each of these, if you measure the doublet separation, gives you phosphorus proton couplings. That is one advantage. So, all these pure shift methods has its own benefits and limitations, and there are many improvements available, and Psyche is the best experiment of pure shift available. If I have not discussed Psyche, there is no time, one interested student can see that. But all these 2D experiments are also come with blend of all these pure shift experiments with the blend of 2D experiments. For example, I can have pure shift COSY, pure shift TOXY, pure shift HSQC, pure shift ROSY, pure shift NOSY, pure shift DOSY, all these experiments are possible. Okay. Simple to show that this is a pure shift HSQC experiment. This is HSQC. See the line broadening coming because of coupling. This is pure shift. See the sharpness of the lines. And look at this one. This is a pure shift COSY. Look at the multiplicity pattern here and here. A simple combination of, it's a blend of two experiments. Combining together is a blend of two pulse sequences, you get a pure shift Cauchy experiment. Similarly, this is a conventional toxi. Look at the broadening of the peaks because of multiplicity pattern. You look at this, these are all toxi with pure shift in both the dimensions, double pure shift toxi. And this is pure shift NOC, this is the conventional NOC, this is a pure shift NOC. Look at the sharpness of this signal. These are all work of our very famous people like Gareth Morris groups and other Manchester groups. They have been doing lot of this type of experiments on pure shift. So with this I can show you another thing from the same group. This is the decay of Cauchy. This is a constant time decay of Cauchy. When you, because of constant time, J evolution is prevented. Look at the sharpness of the peaks here. So many such experiments are possible. So what I want to tell, I will stop here. What I wanted to tell in this class is, there is another type of experiment called pure shift experiments. There are several things we discussed. How do you do the pure shift? Basically remember, pure shift means you break all the homonuclear couplings in a broadband homonuclear coupling, which is a fairly challenging task. I told you, you cannot break the homonuclear couplings in a broadband way and then detect the proton, because it is not possible. It will disturb the magnetization, transverse magnetization. But there are several ways of doing it indirectly, okay, in a two-dimensional way, where what we can do is we can have J refocusing elements in the T1 period. They could be constant time experiment, but decoupling, varieties of refocusing elements are there, all of them can be utilized. Then we can have pure shift in one dimension and the conventional spectrum in other dimension. You can also have direct detection experiment, where you can interrupt the FID at regular intervals, and each interval you can have a J refocusing and get the FID together. It is a real time FID, do the Fourier transformation, no special processing required. Whereas the other type of experiment, pure shift experiment, you have to take the, for a different time periods, there are several experiments I discussed. You have to collect the chunks of FID, assemble it and then do the Fourier transformation. In the direct detection experiment, no need of special processing, okay, and you can do the J refocusing while acquiring the signal, direct detection. And all these pure shift experiments can be combined with many existing well known 2D experiments. For example, 2D Cauchy, 2D Toxy, 2D NOC, 2D DOSI, etc. In each of these things we saw that there is an advantage. We saw a lot of advantages. In the sense, in the Cauchy, HSQC, the signals were very broad because of couplings present, various couplings. But they can be removed with pure shift, and we saw pure shift experiments and pulses and peaks were very sharp. So there are advantages of this. Depending upon what you want to do, I want to tell for you people, depending upon what you want to do. If you want to lose the coupling information, get a better spectrum for analysis, sharp spectrum, you can do one dimensional way also, two dimensional way also, pure shift experiment. Of course, pure shift way, when you do this in a one dimensional way or two dimensional way, take the projection and you can find out that each peak corresponds to a particular chemical shift of inequivalent protons, but you are losing coupling information. But there are several experiments, we can, in the pure shift we can reintroduce coupling. You can measure coupling while using pure shift also. There is a very big article written by us in the progress in NMR spectroscopy that one can, if any of the student is interested, very recently in 2023 we have published that paper that in progress in NMR spectroscopy, one can see that. That is also possible. So what I wanted to tell you in this class is to give a gist of an idea about a new experiment called pure shift, not new experiment which has been in practice for several years, but only few groups are doing, but its utility is enormous. Those who want to use can use this. So with this I am going to stop here. I hope, I think this will be the last class of this course. I wanted to talk about DOSI, again 2D DOSI experiment, where we can utilize diffusion parameter, molecules in a given system. Take a sample in a NMR tube, molecules can be undergoing diffusion because of thermal agitation, and diffusion depends upon various parameters, depends upon the molecular weight, hydrodynamic radius of the molecules, everything, and then we can measure the diffusion by an experiment called 2D DOSI, 2-dimensional dosy experiment, diffusion order spectroscopy, and different molecule based on the diffusion coefficient get separated out. Multiple components can be separated out by using dosy. That has lot of applications also. That if I start, that will be a big topic. I didn't although I was thinking, because of lack of time I could not discuss dosy. But any of you who are interested to learn dosy, you can send me an email. Only special class, only half an hour I can take class to talk about dosy experiment, which is very useful, especially for multiple component analysis. If you are working on metabolomics, you want to find out the components present, different components present in, let's say, body fluid like sugar or urine, you know serum, you can find out by doing this type of experiment, dosy. You can separate out the components based on the diffusion coefficient, provided there is change in the diffusion coefficients. And dosy is done in a very different way by applying field gradients. I have to explain to you how the defocusing take place, how the defocus signal gets refocused. That's a very big topic. We discussed these field gradients, focusing and refocusing in one of the previous courses. But we can adapt the strategy during that time. If the molecules are undergoing translational motion, they are diffusing. So we can measure the diffusion coefficient, and there are several applications of that. So since lack of time, I am not discussing that. I suppose I tried my best to give you whatever best possible concepts and varieties of applications of NMR. Of course, all these things cannot be covered just in 1 hour for each of these topics, like dosy, this Purshift, what I said. Each of these pulse sequences we need to discuss, it can take half an hour each. So, but I would just summary is, you can do this type of experiment, simplify your complexity, which can aid your analysis both in 1D way or combine them, take a blend of Purshift experiment, you can also do it 2D way. So with this I am going to stop here. Thank you very much for all of you for attending this course. Thank you.